Welcome. My name is Gilberto Torres, and today I'll be presenting on the material properties of proton irradiated rat bones. This study was performed under the advisement of Anthony G. Lau at the College of New Jersey. With long-term nemesis on the rise, it is important to understand the effects of radiation on bone health. An increased porosity has been linked to radiation exposure by prior studies. This increased porosity contributes to an increased fracture risk, which may be detrimental to astronauts on long-term missions. Protons can make up about 85% of galactic cosmic radiation. This study will look at the effects of proton radiation on material properties. So why does the radiation affect humans on Earth? The Earth's magnetic fields protect us from radiation. The charged particles are trapped in high-energy region known as the Van Allen belt, as shown in the image. For moon missions, the departure trajectory is aimed towards the North Pole, where these belts will weaken. The effects of radiation exposure can be easily modeled in a controlled environment and may help us understand the effects of bone health from Mars and beyond. For this study, all live animal work was performed at Johns Hopkins University in Brookhaven National Lab. Rats were irradiated at the femoral head only. Controls were sham irradiated. Rats were exposed to 10 centigrade, 25 centigrade, and 100 centigrade proton radiation. They were indented at the anterior, medial, lateral, and posterior locations of the femoral head. For material testing, microindentation was used to obtain the long time and instantaneous shear modulus. MATLAB was used to fit stress relaxation as an exponential decay function, where the shear moduli could be derived. For statistical analysis, a mixed model was used, which is appropriate when one or more factors are considered random. As a result, no significant differences were found in between radiation groups, shown by the left two graphs. A significant difference was found between locations for long-time shear modulus, shown on the right bottom graph. A high variance was observed in the control group. This is common with biological samples. Although no significant differences were found in between radiation treatments, a general downward trend can be observed as dosage increases. From this, we can infer that radiation seems to have a negative effect on shear moduli. This may be due to the deterioration of the organic matrix. The differences in anatomical locations can be explained as such. The anterior region of the femur is typically in compression, whereas the posterior is mainly in tension, resulting in different loading patterns. For future work, a combined study of galactic cosmic radiation and how the suspension should be performed. This will better represent the environments astronauts will be exposed in space. Material properties of these effects have been greatly understudied. Also, a look at systemic responses to radiation may help to pinpoint the factors directly contributing towards the decreased material properties. A possibility could be to look at PTH, which influences osteoclast differentiation. Yet we don't know how this pathway is affected under irradiated conditions. I would like to give a special thanks to the New Jersey Space Grant Consortium and CCNJ Muse. Thank you.